Our pre-lab lecture. So today we'll be looking through lab 15, which is the Diels Alder reaction. In terms of bond forming reactions and significant reactions in the field of organic chemistry, the Diels Alder is probably up there with one of the more important organic reactions, both in terms of its ability to simultaneously form multiple carbon-carbon bonds and to form carbon-carbon bonds with stereospecificity. And this exquisite stereospecificity is a hallmark of the Diels Alder reaction. So, fundamentally, the Diels Alder reaction is a concerted pericyclic reaction between a diene and a dienophile, where two carbon-carbon single bonds are formed, and in effect, we are using two of our carbon-carbon pi bonds, and we're using the electrons in those pi bonds to form these two carbon-carbon single bonds. The beautiful thing about the Diels Alder reaction is it allows us to set multiple stereocenters with stereospecificity. And now you may say, in this reaction, we would get two different stereoisomeric products and their enantiomer. Now, the interesting thing about the Diels Alder reaction is even though you theoretically would get a mixture of stereoisomers, the endo product and one of these stereoisomers is disproportionately favored in the Diels Alder reaction. And as a result, the Diels Alder reaction is quite useful to set multiple stereocenters with stereospecificity. The question in the chat, for this particular substrate, this is based on the electronics of this particular substrate. And the fact that in this case, the orientation of the diene and dienophile is set in a way to account for the relative positions that are electron rich and electron deficient in the diene and the dienophile. Did that answer that question in the chat? Okay, so as I mentioned, the Diels Alder reaction there may have been a slight difference in the position of this OR group and the position of the electron-rich group, or the substitution of the diene in the example during office hours. So generally, when we look for these substrates, in this case, although you would expect the onset that you can get either of the two regioisomers, the electronics of the diene and dienophile influence and determine your regio control. And that's another important aspect of the Diels Alder reaction. It not only allows you to form carbon-carbon bonds with stereo control, but also it provides you regioselectivity based on the electronic character of your diene and the dienophile. Does that answer your question? We'll talk about electronics of the diene and dienophile once we've covered chapter 21, as that's somewhat related to the electronics of unsaturated and alpha beta unsaturated ketones and esters and the electronics of enolates. Okay, so Just to recenter everyone here, the Diels Alder reaction is a useful reaction to form multiple carbon-carbon bonds simultaneously. It's a concerted pericyclic reaction, and it's wonderful for setting multiple stereocenters with stereospecificity. Although at a first glance we would expect to see a mixture of diastereomeric products, the Diels Alder reaction is uniquely selective for a single stereoisomeric product known as the endo product. What we're going to talk about now is the reason why the endo product is preferred, and we'll talk about why the Diels Alder reaction is run under high temperature conditions and it requires heat to go to completion. So, the Diels Alder reaction fundamentally is a concerted pericyclic reaction. In any bond forming event, in any concerted bond forming event, we need constructive orbital overlap. So for example, when we have a bonding interaction, fundamentally, we have an overlap between regions of the same phasing. We have constructive overlap between our p orbitals, right? So if we're making a pi bond, the regions of the same phase overlap constructively, right? If we're looking at an anti-bonding interaction or an interaction that would not productively form a bond, we have attempted overlap between regions of opposite phase. Does this first idea make sense? What kind of orbital overlap and orbital interaction do we need to form a bond? We need regions of the same phase to overlap and interact, to have a bonding interaction. Does that make sense? Does that first idea make sense? Okay, so just like we represented, for example, aromatic systems using molecular orbital diagrams, we can also draw molecular orbital diagrams for normal conjugated alkenes. So in this case, we have our p orbitals as part of our pi system, and we can use those p orbitals to generate a series of molecular orbitals. So for our diene, we have 1, 2, 3, 4 p orbitals and 4 pi electrons in this pi system. Does that make sense? Okay, so if we think about the energy and phasing in each of these molecular orbitals, the lowest energy molecular orbitals contain the least number of nodes. And as we increase in energy, as we move to the higher energy molecular orbitals, we begin to see an increasing number of nodes, which are regions where there is no orbital overlap because there are two adjacent regions of opposite phase. So the more nodes we have, the less we're able to have a contiguous region of overlapping, similarly phased orbitals. And as a result, we're less able to effectively distribute our electron density over multiple atoms in that conjugated system. So the more nodes we have, the less efficient orbital overlap that we have, the higher in energy this molecular orbital will be. And as we go up in energy in our molecular orbital diagram, the higher energy molecular orbitals have more nodes. Each time you move up to a higher energy molecular orbital, you see an increasing number of nodes, or more correctly, an additional node. Right? So here's our lowest energy molecular orbital, 0 nodes. Our second lowest energy molecular orbital has 1 node. And that's part of why it's higher in energy. Does that idea make sense? Okay, so The highest occupied molecular orbital, or the HOMO orbital, as the name implies, is the highest energy molecular orbital that contains electrons. And as you see, when we fill in our molecular orbital diagram with our 4 pi electrons, the second lowest energy orbital is going to be our HOMO orbital. It's the highest occupied molecular orbital. Does that make sense? Okay, now continuing on from this, looking at our diene, we can also look at the Lumo orbital, which is the lowest unoccupied molecular orbital. In this case, the Lumo is the next highest energy orbital, which has 2 nodes. We can repeat this process of drawing a molecular orbital diagram for the dienophile, which is our alkene that reacts in the Diels Alder reaction. The dienophile is overwhelmingly electron deficient, as that helps promote an efficient Diels Alder reaction because it helps tune your dienophile LUMO energy for effective orbital overlap. Okay, so we have 2 pi electrons. In this case, our HOMO has 0 nodes and our LUMO has 1 node. Okay? So we now have the HOMO of the diene and the LUMO of the dienophile. And one thing that I'd like you to notice when we look at these 2 orbitals, are they relatively close or far away in energy? Are they relatively close or far away in energy? In terms of relative energy, as drawn in this diagram, if vertical height is proportional to energy, if just the vertical position, and we compare the HOMO and LUMO, so if we compare these 2 molecular orbitals, would we say that they're similar or different in energy? Just these 2 orbitals in a side-by-side comparison, are they similar or different in energy? They're quite similar. They're relatively close in energy. And this is important because one of the criteria for an effective orbital overlap and a bond-forming interaction is both proper orbital phasing, but also that there are 2 orbitals that you're trying to overlap are similar in energy. Okay. So as we can see, the HOMO of the diene and LUMO of the dienophile are close in energy, and they're also properly phased for a bonding interaction. So if we look at the HOMO of the diene and the LUMO of the dienophile, and we draw them out with phasing, and we overlap our diene and dienophile molecular orbitals, as we can see from this drawing, are we overlapping our orbitals in a productive manner? Are we overlapping regions with the same phasing? Do we have the proper orbital overlap needed for bonding? Are we overlapping regions with the same phase? Looking at this drawing, are we overlapping regions with the same phasing and shading? What do we think? As drawn, so we have our HOMO and LUMO orbitals. We've drawn them out with proper phasing. If we overlap our HOMO and LUMO orbitals and we try to engage in a bond-forming interaction, are these 2 molecular orbitals properly phased for a bond-forming interaction? Yes, they are. And the Diels Alder reaction fundamentally involves an overlap between the HOMO of the diene and the LUMO of the dienophile. they're energetically close enough in energy, and their phasing is properly set up for a productive bond-forming interaction. Does this discussion of orbital overlap and molecular orbital theory make sense for the Diels Alder reaction? Well, one thing to note is that the diene HOMO and LUMO dienophile would look almost identical for most Diels Alder reactions. The only thing that changes is the relative energy, which is based on the substitution of your diene and dienophile, right? Fundamentally, though, the diene would always be a 4-electron system, and your dienophile will always be a 2-electron system. Does that make sense? Now, the reason why we talk about this molecular orbital theory not first explains why this reactions run under thermal rather than photochemical conditions, but more importantly, it helps us to explain the stereospecificity of the Diels Alder reaction. Okay, so if we look at the dienophile typically has electron withdrawing groups, right? Everyone sees these ester groups on our dienophile. That's important. The dienophile is overwhelmingly electron deficient. The diene is usually electron rich outside of inverse electron demand Diels Alders. Okay? Now, if we think about this ester is its own pi system, right? And this ester has overlapping orbitals that make up that pi system, right? Does everyone agree on that point? Right. An ester has a conjugated pi system, as we've seen earlier on in this class. And that pi system, well, sure. It's not entirely appropriate to show phasing for the ester pi system, but sure, we can show that they're comprised of p orbitals overlapping, so there's inherently going to be some phasing. Okay, now the important part is because we have this pi system, because we have these orbitals overlapping and present as part of our withdrawing group, when our diene approaches our dienophile, the diene molecular orbitals can interact with the pi system of your dienophile substituents, and we can engage in secondary orbital overlap interactions with the orbitals on your electron withdrawing group. This interaction, although it doesn't form a bond, is a stabilizing interaction that stabilizes the endo transition state. And because we have these stabilizing secondary orbital overlap interactions, we see exquisite stereospecificity for the endo stereoisomer. Yes, yes. Though when you talk about secondary orbital interactions, it gets a little more complicated than just same phasing overlapping. The main thing is the orbitals present in your diene can interact with the conjugated pi system in the electron withdrawing groups on your dienophile, and that can help stabilize your diene. Okay, so does everyone understand the reason why this endo approach, when you're dying approaches to maximize these secondary orbital overlap interactions with your electron withdrawing groups, does everyone see why this endo approach is favored? And why this endo transition state is partially stabilized and favored in the Diels Alder reaction? We'll talk about this exact lab product in a moment. To help us see and to help us visualize the exo and endo products, let's look at the reaction that was actually studied in many organic chemistry teaching labs, which is the reaction between cyclopentadiene and an alkene typically derived from succinic anhydride. So in this case, when we think about the endo approach, as we talked about previously, your diene wants to approach in a way to maximize interactions and these secondary orbital interactions with your dienophile substituents. So as a result, your cyclopentadiene will approach from the same side as your electron withdrawing groups on the dienophile. Now, how does this lead to a unique stereoisomer? Well, if we think about the endo approach and we draw out this approach from a side-on perspective, I'd just like us to look at this cyclic transition state, and I'd like you to tell me a few things. First, if we look at this alkyl group and the hydrogen, are they on the same face or opposite face? The same. And are these groups pointing up or down in this transition state? Up. Exactly right. So the alkyl group and the hydrogens are both pointing up. Looking at our carboxylate groups, are the carboxylate groups and these other hydrogens that we'll label as B, are these carboxylate groups pointing up or down? They're pointing down, right? So as we see, when the Diels Alder reaction occurs, we get a strong preference for this endo product. And the way I like to think of the endo product is this withdrawing groups are tucked on the bottom, almost on the inside face of the ring, almost like an endoskeleton. So does everyone see how the endo approach gives the endo product? Does everyone see how to go from reactants to transition state to product for the Diels Alder reaction? Now let's look at the exo approach. So what's the difference in the exo approach? What's the main distinction in the exo approach? Let's see if anyone notices. What's the main distinction? The withdrawing groups are on the opposite side. In the exo approach, our diene approaches from the opposite side compared to the withdrawing groups. The exo approach and the exo product is minor because this is a higher energy transition state because we don't have any of those secondary orbital overlap interactions. And as a result now, in terms of relative stereochemistry, is this alkyl group and the carboxylate substituent, are these two substituents on the same face or opposite face now? They're on the same. So if we look at the exo and endo product, we can see clearly the relative stereochemistry has changed. Now, the beautiful thing about the Diels Alder reaction is we observe upwards of 4-to-1 selectivity and almost in many cases, you get almost 100% of the endo product. So even though two stereoisomers are possible, the Diels Alder is stereospecific and preferentially yields the endo stereoisomer product. So is everyone feeling a little more comfortable visualizing the Diels Alder reaction and predicting the stereochemistry and structure of the products? Does this logic make sense to everyone? Do these diagrams make sense to everyone? Okay. So let's take a moment. Let's take a moment now. And let's do an example. So I'm just going to clear out. And let's try to predict the product when we have the following diene and the following dienophile. I'd like us to predict the major product from this Diels Alder reaction. So let's work on this example for a few minutes. And then I would love for some students to share their proposed structure of the Diels Alder product as an annotated structure on the class whiteboard. And if you have any questions, don't be shy to ask them in the chat or verbally. And I would pay special attention to the orientation of the alkyl groups on the diene. So the student response looks reasonable. Let's talk through and let's visualize what's going on here. So in this case, we have our endo approach. So our diene is going to approach from the same side as our withdrawing groups. So drawing out a transition state. Let's look and let's try to assign the stereochemistry at each stereocenter. So first and foremost, if we look at these inner groups, this R group and this hydrogen, are these two groups pointing up or down from this endo approach? Do both of them point down? Let me try to help convey what's going on. Well, it's the same structure and it's the same presentation. So just looking at these two inner groups, this R group and this hydrogen, in this transition state drawing, are these two groups pointing up or down? So to help you visualize why these two R groups are not both pointing down, it helps to view this from a bit of a side-on perspective. So let's look and let's refresh this cyclopentadiene example, right? So in this case, both of these quote unquote inner groups, during the endo approach, both of these inner groups end up pointing up. Does that part make sense? So looking at the previous example, we saw from the endo approach for cyclopentadiene, we ended up with both of our alkyl groups as part of this cyclopentadiene. Yes. The main difference between exo and endo is the relative stereochemistry. The point I'm trying to bring up is the fact that looking at our diene, when both of these alkyl groups are quote unquote inner alkyl groups, as part of the endo approach, they end up on the same face pointing up. Does that part make sense? Does everyone see how the relative stereochemistry for the alkene substituents directly translates to the relative stereochemistry in the endo product? Does that first part make sense? Well, as a general rule of thumb, you can separate and you can look at both the inner and outer alkyl groups on your alkene. Now, to help you visualize this from a side-on perspective, I tried to draw one of the side-on perspectives here. Yes, the sp2 carbons are flat, but as part of the Diels Alder reaction, when we're forming these carbon-carbon bonds, depending on the configuration and orientation of the alkene, we get different stereoisomers. And in this case, we're looking at an example where our inner substituents are different substituents. So to help redraw this, to make it a little bit easier to see this side-on approach and to help us make it a little bit easier to help understand why these inner substituents are pointing up. Let me draw this a little bit more suggestively. Okay, so when your diene approaches the dienophile, the approach occurs endo from the same face as your withdrawing groups. Okay. So as part of this approach, what we can see is from this side-on view that I drew previously, the R group and hydrogen on these inner positions end up being forced up during the approach. The outer hydrogen and R group end up pointing equatorial down as a result during this approach. So as we can see, depending on the configuration of the alkene, we get a different set of stereoisomeric products. So the alkene stereochemistry directly translates into our product stereochemistry. And that's why, as we note, the R group is pointing up on the top and down on the bottom. Does that make sense to everyone? How the alkene geometry translates into our product stereochemistry? Because the alkene is flat, it's a little tricky to give it the right three-dimensional view to help you see how this R group is up. Well, you can also get the enantiomer as well. We're just looking at one of the stereoisomeric products. And it's important to carefully note the configuration of the alkene in order to accurately draw out the product stereochemistry. So now that we've assigned the relative stereochemistry of these R groups, let's assign the most important stereocenters, which are the stereocenters for these two carboxylates. So for these carboxylates, are they pointing up or down based on this approach and based on this transition state drawing? Are these carboxylate groups pointing up or down? They're pointing down, exactly right. So this is our endo product. And the main thing to note for the endo product is we've set the relative stereochemistry between our alkene alkyl groups and the electron withdrawing groups on our dienophile. So we get the following product plus the enantiomer. Does this example and do these drawings help us visualize why we observe certain stereochemical outcomes and certain products from the Diels Alder reaction? So it's important to carefully pay attention to the substitution pattern and geometry of the alkenes on your diene to help correctly assign the product stereochemistry. Does this example make sense to everyone now that we've gone through it together and viewed the drawings together? Okay, so in the context of today's laboratory, we're looking at the Diels Alder reaction between anthracene and maleic anhydride. So the important thing to note for anthracene, our diene consists of these middle alkenes. First, because these alkenes are generally the most electron-rich alkenes in this molecule, and also because if you draw out the resonance structures, these alkenes have a lot more isolated sp2 character compared to other alkenes in this anthracene molecule. So the middle diene in anthracene reacts similarly to other isolated dienes. Maleic anhydride is a symmetrical activated dienophile, and our diene is going to approach following the endo approach. We'll form two carbon-carbon bonds, and as a result of the endo approach, we get the following maleic anhydride adduct. One thing I would note is when this central diene reacts, we're able to retain a large amount of aromaticity in anthracene because we generate two isolated benzene systems. So does everyone see the mechanism and stereochemical outcome for this reaction? Does everyone see why we get this product out from the Diels Alder reaction? Now, this compound is so incredibly symmetrical that there's a high degree of symmetry, and as such, we generally only see this single endo product. We don't have to worry about substitution patterns because both our diene and our dienophile are perfectly symmetrical. So once we isolate this Diels Alder adduct, and we generate this Diels Alder adduct over the course of our reaction, we'll be able to isolate our product via filtration, rinsing with ethyl acetate, and then a formal trituration with ethyl acetate in a Craig tube. From there, we're going to characterize our product via IR, where we'd be able to note the aromatic CC and CH stretches and the carbonyl CO stretches. We'll be able to record the melting point of our product, which will be a unique identifier that we've isolated the pure Diels Alder adduct. And finally, we'll perform the ignition test, which will confirm and verify the presence of an aromatic group. Further, we'll also perform the ignition test on a range of organic compounds just to help you get a sense of what ignition test results look like for different aromatic and non-aromatic compounds. So in terms of practically, this Diels Alder lab and the substrates have been chosen to help minimize issues with different stereoisomers being generated, different regioisomers being generated, and we generally only isolate this single product from the reaction. We'll characterize the product using 3 standard methods: spectroscopy, physical property measurement, followed by chemical tests. And then we'll summarize the yield and purity of our product using this data. That's fine, and IR and KBR will be more than sufficient for matching. In the video, I believe that after the rinsing, when I took a measurement for its purity, I found it was sufficiently pure that it didn't need that secondary purification step. To answer the question, shouldn't you expect a little bit of the exo product? What I would say is I would draw the structure of the exo product and see if it's actually different. This product, these substrates are highly symmetrical, and this product is highly symmetrical. And I would try to draw the exo product and try to rotate it to see if it's truly different than the endo product. Did that answer your question? Perfect. So if we don't have any other questions, what we'll do is we'll archive this recording.